All right, analysis. It is time for the last two tests. Among these two tests, you will experience the perfect test. Well, the almost perfect test. And you will also experience its, I guess one could call it a corollary, the root test. So we will be looking at the ratio test today. Hashtag ratio test is the best test. We'll check out some Twitter stuff there at the end. I'll add that. After we look at the ratio test and all its glory, we will look at an example. We'll do the proof. We'll look at the root test. We'll do an example. And then we'll get out of here. All right, but without further ado, let's go ahead and get started with the almost perfect test. The ratio test. So, what does it say? Let the following series be a it's not Pokemon, non-zero series. With that said, the first of three consequences of the ratio test is the series converges absolutely. All right, well, we talked about what it means to converge absolutely. It means if I take the absolute value of this, that too will also converge, which is pretty sweet. This converges absolutely. So if it's alternating, it'll still converge. If the limit as n goes to infinity of a sub n plus 1 over a sub n is less than 1. Period. Wait, what? That's it? No preconditions? Just put two successive terms in ratio, look at its absolute value as n goes to infinity. If that's less than 1, the thing converges? Absolutely. No this? Oh my god. This is the best test. What's the second of the three? The series diverges if the limit as n goes to infinity, not m, n, whoop, drop my pen, n goes to infinity of successive terms is greater than 1. If I put two successive terms in ratio and look at the absolute values and goes to infinity, if that's bigger than 1, I'm done. No preconditions. Oh, I'm having flashbacks to the integral test when we had to check decreasing, we had to check always positive, we had to check continuous. Oh, it was miserable. And we had to do an integral. The ratio test, I just have to take the sequence that the series is composed of, put it in ratio, and look at its relationship to 1. This is the best test. What could possibly be bad about this? What's the third one say? If the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to 1, the ratio test is inconclusive. This is almost. Oh well, this is the ratio test. This is the almost best test. Hashtag ratio test, the best test. Boom. Ratio test is the best test. Let's go ahead and slap that on like every page. Boom. 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 All right, I'm going to slap that on the rest of the pages, but I won't make you guys watch it. And we are back. You know what? I'm going to go ahead and change the color to a nice, let's do like a lighter blue so that the ratio test is the best test hashtag and the page number pops. All right, let's get our first example going so that we can learn to use this amazing test let's try to determine if the following series converges or diverges. Ugh, factorial, those are awful. And exponents, this sounds terrible. Wait, let's use the ratio test. Hashtag ratio test is the best test. All it says is that we need to look at a sub n, which is 5n over n factorial. We need to look at a sub n plus 1, which is 5n plus 1 over n plus 1 factorial. We need to look at these two things in ratio and look at its value. If it's less than 1, it converges. If it's greater than 1, it diverges. Let's go ahead and look at this thing. The limit as n approaches infinity of a sub 1, a sub n plus 1 over a sub n. So we have 5n plus 1 over n plus 1 factorial divided by, I'm going to just multiply by the reciprocal, n factorial over 5n. This is all absolute value. All right. Hopefully things will simplify nicely. It looks like they will. We have 5n plus 1 over 5n, which means the 5n's are going to go away, and we'll have 1 5 on top. Oh, sorry, no, we're going to, 1 5 on top. And then we have n plus 1 factorial and n factorial. This n factorial is going to cancel out all but 1. The final n plus 1. Boom, we have this. And this goes to 0. Let me go ahead and just, for continuity's sake, throw some absolute values around that. I do know that n is greater than 1, so I don't really need the absolute values, but I'm going to include them just to be safe. This is going to 0, right? By the ratio test. By the ratio test, the series 5 to the n over n factorial converges because the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to 0, which is less than 1. All right, that's all we need to check. There are no preconditions. Hashtag ratio test is the best test. Let's go ahead and look at a second example. How about the series n squared minus 2n plus 6 all over n to the 5th minus 8n? I will say, before I do anything, the ratio test is the best test because it can handle really difficult series. But I always like to check the nth term test first. And this thing is going to 0. The sequence here is going to 0 as n goes to infinity. So it does converge. If it didn't go to 0, I would have said this diverged by the nth term test a while ago. So I just want to say that. Don't always go to the ratio test because the first test, at least you should always consider thinking about, is the nth term test. So let's look at a sub n plus 1, put them in ratio, and see what happens. Can the ratio test maintain that best test status? All right, the limit as n goes to infinity of a sub n plus 1 over a sub n is, all right, and I always like to do that reciprocal strategy that I previously did. This is going to be the limit as n goes to infinity of this thing with plus 1's everywhere, n plus 1 squared minus 2 n plus 1 plus 6 all over n plus 1 to the 5th minus 8n plus 1. This is going to be multiplied by, I'm dividing by the a sub nth term, which means I'm multiplying by its reciprocal, n to the 5th minus 8n over n squared minus 2n plus 6. Make sure you understand why I'm doing this multiplication rather than division. Before we go distributing anything, let's just think about how to determine if a rational expression its limit, you look at its largest power, its leading term. So let's see. If I were to distribute everything, the top would have an n squared times an n to the fifth. The top would have an n to the seventh. All right, so this is the limit as n goes to the infinity of n to the seventh plus a bunch of junk over the bottom would have an n to the fifth times n squared. This is also an n to the seventh plus a bunch of junk. So the limit as n goes to infinity of and beyond of a sub n plus 1 over a sub n is 1. Uh-oh. It's equal to 1. What did the ratio test say? The ratio test is inconclusive. Ratio test, you told me you were the best test. Are you telling me I can't use you to figure out the limit of this thing? What do I do? Do I do the integral test? I don't know what to do. Let's think. We have the... So the ratio test is not going to work here. This is very unfortunate. The best test fails us here. Maybe it doesn't deserve that title. We could... Nth term test doesn't tell us anything. Right? It tells us that it doesn't diverge. Well, sorry, no. The nth term test tells us nothing. This could be a telescoping series, but my intuition says it's not. Definitely doesn't look geometric. Maybe we could use a basic comparison test or a limit comparison test. Maybe. That might be a good avenue to move to next. I'm definitely, I know you hate to hear me say it, but I'm feeling an integral test here because I can do some partial fractions on that thing, take some easy integrals. I know it's not ideal, but it's definitely eventually positive. Its parent function, the function that models it, is going to eventually be continuous. Yeah, I'm feeling... Well, whatever. If you think we should use something different, throw it in the comment section below. I haven't done that in any video so far, but go ahead and let us know what you think we should solve this one with, because the ratio test and its glory has failed us. Sticking to my guns, though. Hashtag ratio test is the best test. Let's look at a proof of the ratio test. The ratio test. Proof. Very redundant here. All right, in this proof, we are going to start by looking at what if the limit is less than 1. So the ratio test gives us that. All right, so let a sub n be a series that is non-zero. We want to avoid those undefined and zero ratios. Let the series be non-zero, right? And let the limit as n goes to infinity of a sub n plus 1 over a sub n be less than 1. We're going to show that this implies convergence. We want to show this implies convergence. All right. So if the limit as n approaches infinity of this thing is less than 1, then it equals something. So let me go ahead and write that. I'm going to go ahead and use a new color. I'm trying to be a little bit more colorful here. The limit as n goes to infinity of a sub n plus 1 over a sub n. Let's go ahead and say it's equal to L, which is less than 1. I think a picture helps. Here's a number line. Here is the number 1. And here is our number L. Right? What is the definition of a limit? The definition of a limit says that if I go out far enough, I will eventually be as close to L as I want, and then from there on out, I will be within that interval. let's go ahead and say the interval is right here. Right? If I go out far enough, this value is eventually going to be in this interval. Somewhere. I don't know where, but it's going to be somewhere in that interval. Right? We could call this like L plus epsilon. We could call this L minus epsilon. Call this distance epsilon. For some value n, at some point, this value, a sub n plus 1 over a sub n, is going to be, of course, bigger than 0, but it's going to be less than L plus epsilon, which is also less than 1. Right? At some point, this absolute value expression is going to be in this interval. That's like for without loss of generality, just for arbitrary reasons. Let's say that this is a sub n plus 1 over a sub n. It is greater than 0, and it is less than L plus epsilon, and it is L plus epsilon is less than 1 because L is less than 1, and epsilon can be as small as we want it to be. We have this extended inequality. 0, the absolute value of a sub n plus 1 over a sub n is less than L plus epsilon, which is less than 1. This is the key to our proof. I'm actually missing a bit in this little explanation. Let me go ahead and add it. Just going to move that thing over. Cool. For some value n, for all n greater than that value n, this inequality holds. This is our definition of a limit. Right? For some value n will eventually be in an interval. And then because we're in that interval and because of our assumptions, this inequality is true. Right? The key is that 1 right there. All right, I'm over explaining. I'm going to go ahead and take this inequality to the next page. All right, so this number, L plus epsilon, and the fact that it is less than 1 is the key to our success. I actually want to hone in on this part of the inequality. Let's let n equal n. With that said, we have the following inequality. What is this inequality saying? Just a quick check so we understand as we proceed what we're doing. It's saying that at some point n, and this is the first point, at some point we will be less than epsilon, L plus epsilon. At some point, capital N, oh, this should be an equal sign, by the way. Our first point at which we are less than L plus epsilon, which is also conveniently less than 1. Right, that's what this thing means. At some point, we will be less than L plus epsilon, definition of a limit. All right, here's the trick. This implies, now keep in mind, L plus epsilon is less than 1. Right, I'm going to multiply both sides of this inequality by the absolute value of a sub n. So we're going to have a sub n plus 1 is less than or equal to L plus epsilon times a sub n. And remember, L plus epsilon is less than, just as a reminder, this is less than 1. All right, now let's let n be equal to n plus 1. All right, for any n, small n, greater than n. So this is, in fact, greater than n. We're going to let n equal that. The inequality is true. So a sub n plus 1 plus 2 over a sub n plus 1. This is less than L plus epsilon. All right, this is just saying the definition of the limit. Once I get past that value capital N, I will be less than L plus epsilon for evermore. Right? What does this thing say? Well, this implies a similar inequality. A sub n plus 2 is less than L plus epsilon times A sub n plus 1. Now I'm going to take what I've just written and I'm going to write it down here, and I want you to think. A sub n plus 2 is less than L plus epsilon, which is a number less than 1, times A sub n plus 1. Right, but what is A sub n plus 1 less than? It is less than L plus epsilon. That's this L plus epsilon. It is less than L plus epsilon times A sub n. All right, and I'm about to erase this L plus epsilon, one of these L plus epsilons, because it's just L plus epsilon squared. Sorry, this is taking a second. Boom. L plus epsilon squared times A sub n. If I continue this pattern, right, the next one's going to be A sub n plus 3 is less than L plus epsilon times A sub n plus 2, which is going to be less than L plus epsilon squared times A sub n, capital N, plus 1, which is less than L plus epsilon cubed A sub n. Interesting. If I continue this pattern, which I'm going to do on the next page, A sub n plus m is going to be less than L plus epsilon to the m times the absolute value of A sub n. Let me write that, especially since I'm using the inconvenient letter m, m as in Mary. I have A sub n plus m is going to be less than L plus epsilon to the m times A sub n. Well, I have these two sequences. So their series are less than each other. Right, in these two series that I have, m is the thing tending to infinity. But if I can figure out if this thing converges or diverges, that will tell me whether or not A sub n converges. Why? Because for the first n minus 1 terms, you have a finite series. Of course, it's going to be a number, right? So the divergence or the convergence of this thing is going to be the same as the divergence or the convergence of this thing. Let me actually write that. They are the same series, except one has a bunch of the initial terms cut off, that being the first one. With that said, let's hone back in on this thing. Why must the left-hand side converge? It is less than this thing. If this thing converges, then by the basic comparison test, this thing must also converge? Does this thing converge? What's L plus epsilon again? L plus epsilon is greater than 0, but it's also less than 1. A sub n is just a number. This is less than 1. This thing converges. By the geometric series test. Less than 1, repeated multiplication. This thing is going to converge by the geometric series test. Therefore, must converge by the BCT. Therefore, a lot of therefores. Must converge. One last therefore. Oh my gosh. The best test, the ratio test, is really just the geometric series test. It's really just the BCT, and it's really, oh my god. The best test is really just all the other tests hiding, except for the integral test and some other tests, but the integral test. I'm not a fan of the integral test, so I just got to point out that it's not here. The ratio test shows convergence if the ratio is less than 1. What would happen if the ratio is greater than 1? Let's quickly go back. If the ratio, if L is greater than 1, then I'll have Q. I can put an interval around that. I can have my ratio there. And I believe all of these things are going to kind of flip-flop. I'm going to have 1 is less than a sub n plus 1 over a sub n, which is less than q. Or in this case, I could say, actually, I want to write it this way. L minus epsilon. L minus epsilon is less than a sub n plus 1 over a sub n, which is less than q. All right, and if I continue this, I'm just going to end up having a bunch of flip-flopped inequalities with some minuses. Flip-flop, minus, flip-flop, minus, flip-flop, minus. Boom, 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 boom. The point being, when I get all the way over here, I'm going to have this. This number is strictly greater than 1. And so my sequence is greater than a geometric sequence that has ratio greater than 1. So this thing will diverge, forcing this thing to also diverge. All right, the reason why I'm doing this is I'm not going to do the second part of the proof. I'll leave that to you if you so desire. But if we switch it to becoming larger than 1, the ratio is larger than 1, then our sequence that we care about, our series that we care about, is going to be larger than a diverging series. It is also going to, in this case, diverge using the basic comparison test and also the geometric series test. The ratio test is the best test. And then there was one more test. Let's go back to blue. There was one more test. It's like a little sibling of the ratio test, the root test. It's pretty nice, not gonna lie. It's convenient in certain scenarios. Right? The proof is very similar to the ratio test, but the root test, sometimes it makes the algebra nicer. Let a sub n be a series. The series a sub n converges absolutely if the limit as n goes to infinity of the nth root of the absolute value of the sequence is less than 1. It's basically just the ratio test, but with a different expression. We don't have a ratio, we have a root. Right? B, the series diverges if the limit as n goes to infinity of the nth root is greater than 1. And just like the ratio test, if a sub n, if the limit as n goes to infinity of the nth root, the absolute value of the sequence, is equal to 1, the root test is inconclusive. I'll let that one marinate for just a second as I prepare my example. All right, we are looking at the nth root of the absolute value of the sequence rather than the ratio of successive terms, as the ratio test has us look for. All right, here is my root test example. So we have n to the 5th plus n cubed plus 8 all over 2 times n to the 8th plus 3n plus 1 all raised to the n. Right, when is it good to use the nth root test? When you're raising things to the nth. Right? Otherwise, I probably would use the ratio test, but this will appear every now and then. This is not an uncommon series that will pop up. All right, so what do we want to do? We want to use the root test. All right, the root test and the ratio test are amazing tests. All you got to do is check the limit. In this case, the limit as n goes to infinity of the nth root of our sequence I might add real quick that the nth term test tells us that this thing converges, so it may or may not converge or diverge. If this was not 0, then it would diverge, we would have done. All right, think about the nth term test first, every time. All right, this is going to be the limit as n goes to infinity of the n and the nth root and the nth power are going to cancel each other out, and we're going to be left with the absolute value. Boom, and then this limit goes to 0. Okay, we have an 8 in the denominator, 5 in the numerator. This thing goes to 0. So, by the root test, our series, that is not how you spell our series converges because 0 is, of course, less than 1. All right, root test is nice when you are working with series of which its sequence is raised to the nth power and similar things like that. The ratio test otherwise is a pretty darn good test, except when that thing equals 1, because that is unfortunate. Right? But that is the best test, and the best test sidekick, the root test, the ratio test and the root test. All right, what did we do today? We looked at the ratio test and its glory. We did a couple examples. Let me throw an S there. We did 2 examples, one of which converged and one of which was inconclusive. We did not end up figuring out whether or not that thing converged or diverged. Or we did the proof, and the proof is a little bit complicated, but it was really just the geometric series test and the basic comparison test. in disguise. The perfect test is really just the basic test. Then we looked at the root test, did an example, and I'm going to close this video out with some excellent tweets from years past that touch on how the ratio test is the best test. Have a good one, guys.